So online algorithms are a great way to capture decision making under uncertainty. So we want to make a decision, an algorithm wants to decide about something, and we don't know what's going to happen in the future, and you want to capture that through this concept of online algorithms. And the simplest model, inputs arrive one by one, and you have this algorithm that looks at this input and it wants to decide something. We'll come to the exact examples of what these decisions could be. And once it makes a decision, it cannot undo it. It's kind of committed to the decision. And we want to design algorithms that sort of do the best without knowing what's going to happen in the future. This is the online algorithm setting. And if you take a step back and ask the question, what is this framework trying to achieve? It's basically handling the unknown, right? So we have some things going to happen in the future. We don't know what they are. And we want to design algorithms that can cope with such uncertainty. So the online algorithms is one way of doing it. So they assume that the future is fully unknown. So the typical computer science fashion or like algorithms fashion, they assume the worst possible case. Now anything can happen in the future, and you want to design algorithms to hedge against that. So that's the paradigm in online algorithms. And consequently, the bounds that these algorithms tend to achieve are rather pessimistic because they have to work in pretty much every possible scenario. And therefore, it's also hard to exploit patterns that occur in data because they, again, like they operate in the worst case. And this paradigm has been studied for typical resource allocation problems like caching. Imagine pages arrive one by one, and you want to decide which ones to keep in the cache. Or scheduling, you have jobs arriving in a sequential order, and you want to decide who to allocate to which machine, and other optimization problems. That's a traditional line of thinking here. And on the other side, we have machine learning, and I want to contrast these two fields in the best possible way. The whole tenet of machine learning is to exploit data or history, right? So we have enormous amounts of data collected over time, or you have some postulate on the behavior of the system, and you want to capture that into a robust model that can be used to predict the future in some sense, predict things that are not seen before. Right? That's a whole paradigm in machine learning, summarized in a very layperson. So because of the way they exploited data or history, they tend to have a good on average performance. Algorithms in machine learning, they work great on typical data. But on the other hand, we all know examples of where ML fails badly because they are not very robust to outliers, or in some extreme cases, even to some small perturbations in the data. Right? They tend to break down when these things happen. And machine learning has been used, of course, for many things. And the context that we are interested in, they'll be used for like in caching setting, which page is going to come next, or how long is a job for scheduling, and so on. That's the kind of questions that we use machine learning for, not for the language models. Okay, good. So that sets a stage for like two kinds of algorithms, like online algorithms, machine learning. Both of them have the commonality that they handle uncertainty in the future. So to make it a little more concrete, like how do we measure the performance of such a system? So the classic metric used in online algorithms is competitive ratio. So it's typically used in combinatorial settings. So the measure there measures the performance of an algorithm against an offline adversary, offline algorithm. An offline algorithm is one that knows everything about the future, but doesn't have any uncertainty built into that. So you measure the algorithm's performance over the optimum, which is the offline algorithm performance, maximized over all instances. And that gives you like a multiplicative quantity, which is known as a competitive ratio. How well this algorithm performs against an offline algorithm that knows everything. And there's another quantity which probably is like less known or less studied in traditional like TCS communities, is regret, which is used in machine learning settings, where you measure the performance of an algorithm again in the online fashion against a class of benchmarks, right? Benchmarks, I mean that algorithms with some fixed rules or fixed restrictions. We look at that. So there the quantity, the measure of performance is measured against like algorithm performance. minus this benchmark on this instance. Okay. That's the regret measure in machine learning. This is known as excess loss and other things like that in typical statistical learning settings. Excess risk. Okay, so we'll focus on the online algorithm settings and we'll try to see what this learning augmented means. So the overarching question is, can you improve the performance of online algorithms if you have access to some form of possibly wrong information about the future? That's the high-level question that we'll try to understand. Because online algorithms work in the worst case setting, so you don't assume anything about the future. Machine learning models give some idea about the future. Can we marry these two concepts in a meaningful way? So again, you have this online setting, and just before the algorithm makes a decision, what if it has access to some kind of a hint or a prediction or an advice or whatever you want to call it, and can you use that to improve the measure of this algorithm? That's a high-level question that you want to understand. Things are clear, right? Okay, so I want to view this problem space in this following manner. So we have algorithms that play like a central role in determining everything. So there are three kinds of quantities that we typically want to optimize. So one is metrics, another is resources, and the other is what kind of hints. Now this, in my feeling, it kind of defines the problem space, because so far what I've talked about doesn't have any concrete instantiations, and they're like very vague, but let's try to make it a little more concrete. So in terms of metrics, you can design algorithms to optimize either the competitive ratio or the regret. That's one axis or one dimension that to focus on. Next is resources. You can design like online algorithms or learning augmented algorithms to maybe improve the accuracy of a existing algorithm, or to improve or reduce the amount of space it requires. For example, if you are familiar with streaming settings, that's a measure of importance. Or you want to improve the running time of the algorithm. Maybe by knowing something about the future, you can make the algorithms run faster. That's you're trying to optimize certain resources. And the third dimension of interest is the hints. There is no single recipe for here is a hint provided to the algorithm. It can be different types of hints, or you want to have a notion of error, like when do you call a hint to be good or bad, or you focus on the size, how big the hint is, or number of times the algorithm actually asks for a hint. These are all different measures of how much the hints are used by the algorithm. This is another dimension for us. Okay, so now that we have set up the framework here, so we have online algorithms, we have machine learning models can hopefully help the online algorithms. So what do we want to achieve with this? So there are like three basic desiderata that we want to focus on. One is what is called consistency. And the idea is very simple here. If the hints are really good, if they are really able to tell about the future, how well can the algorithm perform, can make use of it, right? In an ideal setting, if the hints are extremely good or even reasonably good, we want near offline performance. Now it's almost as if I know the future with certainty. So in that case, I want the algorithm to go back to an offline type performance. In fact, I want something stronger. So we want something like a graceful degradation of the performance of the algorithm with hints. The hints are extremely good. We want like offline performance, but as the hints start getting like poorer and poorer, we want a more graceful degradation of the algorithm's performance. That's one desiderata, and we call that consistency. The second one is almost a converse. It's the robustness, where we want the algorithm to perform reasonably well, even if the hints are bad. The hints could be random. They could be even adversarial, right? Like you can imagine ML models can provide adversarial advice to the algorithm. Even if that were the case, we don't want the algorithm to throw up its hand and say, sorry, you gave me bad advice, so I'm allowed to do anything bad. So we want them to regress, or we want them to fall back to a online performance, even if like hints are bad at every time. That's it's almost like an asymmetric setting. And the third desirable property of these things is what I call parsimony, where the algorithm should use hints only when it's absolutely required to. You know, just because I get a hint, I shouldn't be asking every time, you know, please help me, right? Because the ML models could be very expensive to run or may not be available at every time step. So you want these algorithms to really use the hints when they are absolutely necessary. And if it's not needed, the hint, then it should just go as usual. That's another property. But at the same time, we should not compromise on consistency or robustness. So they should still remain consistent and robust. And the main motivation here for parsimony is the hints can be expensive to obtain in general. Like if you consider like large machine learning models, they tend to be expensive to do inference or to do prediction. So therefore, we want this property to hold. Good. Any questions at this point? Good. Another important factor is that the algorithm should not make any assumptions about the prediction. It should not assume that the prediction has some certain property or the prediction errors are of certain kind and so on. So they should be oblivious to the kind of errors that the predictions can make. All right. So to give you a concrete example of a problem, I'm sure like some of you have seen this already, but nevertheless, it doesn't hurt to look at this again. So this is a classic binary search problem. So all of us know what binary search means, but just to set the notation correct. So we have an array A that's sorted, it has n elements, and you have a query element Q. And the goal is to know if, or actually goal is to find the index of this element, query element in this array, if it exists. So what we do is we of course start with the middle point, compare array is sorted. So it tells me which way to go, left or right, and then keep doing this and until I hit the element, if it's there. And the number of probes into this array is log n. That's the measure that we focus on. And we want to understand this problem to see whether hints or advice can help here. This is not strictly an online problem, but again, like it gives an idea of what this model can achieve. But this is the binary search with hints, and it is an original take of Lecoq and possibility. And what is a hint here? The hint just gives you, okay, you ask this query, and here is an array. I tell you for this query, I think it's in the 17th position. That's a kind of a hint. So it gives you index of the query element Q. So suppose the algorithm gets this, how can it use it to improve its performance? So what it does is, first of all, it compares the query with the position that the hint suggested. If the element is there, great. My hint is perfect, you're done. Otherwise, you do like a doubling trick, right? You start with the if the query is more than the that element of the hint's suggestion, then you do like a doubling. You probe the array for like at the second position, fourth position, eighth position, so on. You try to kind of bracket that element into this increasing intervals. And then once you find an interval where this query element is potentially there, you do a binary search inside it. It's a very, very simple natural algorithm. And you do the other way when Q is less than A of H of Q. So this is how you use the hint. Okay, the algorithm is simple. But what can we tell about its performance? And here is a key point. Suppose T of Q is a true index of the element Q in this array. And remember, H of Q is a hint that the oracle provided. And so you can measure the error as the difference between these two, how far the hint was away from the true element. The first observation is that the hint is here and the true element is not here. You only need log of this error to actually find this large enclosing interval, because you do doubling trick every time. So you only expend like log of this error. And once you're inside this large interval, you only need further log more to actually do binary search to find if Q really exists. So we're talking about 2 log epsilon. And the key point to notice is that if epsilon is really small, the hint was accurate, then instead of log n, you would incur the number of probes is like log of some small number. So which is great, right? And it's also robust because the hint can be, every element can be like position n or something like that. You can just throw, the hint can try to throw the algorithm off. Doesn't matter. You still won't make substantially more number of probes. You'll get like 2 log n probes as opposed to like log n probes. So it is fairly clean. Okay. This is how you would use hints with binary search. So let's look at a slightly more online and slightly more non-trivial problem, which is a ski rental problem. I'm sure like most of you know ski rental. Maybe not so much in San Diego, but so a skier wishes to ski for like say X days. They don't know what X is. They don't know how long they're going to like skiing and so on. And they have a choice. Every day, either they can rent a ski for $1 or they can buy skis for $B. B is more than 1, of course, and ski free after that. Right? Once they buy the ski equipment, they can ski forever. And the decision that they face is mentioned by the ski. And the thing, this is a very classic rent or a buy problem, right? I mean, we face this in every like daily life situation. Should I, buy a house, or should I, rent or buy services from the cloud, or should I buy a annual subscription to like a public transit? Right? So should I buy tickets one by one, or should I just buy a monthly pass? It's a very common scenario. And what makes it harder is that X is not known. I don't know how many days I want to ski, or how will I even like skiing after like X days. So if this amount X is known in advance, the problem is trivial, right? Because if X is more than B, I know that I'm going to ski for 10 days. The ski costs $7, so I'll just buy the ski. Right? Otherwise, the ski costs $7. I'm going to ski only for 3 days. I just rent every day. It's a trivial solution. And the question asked is, what if X is not known? That's the uncertainty here. And there's a classic deterministic algorithm that solves this problem, solves in an approximate sense, which is if the skier wishes to ski for X days, what the skier can do is they buy the ski on the beat visit. On the 7th day when the ski is like $7, and the 7th day I buy the skis. And if I rent for the first 6 days. And the claim is that you never spend more than twice the cost of skis doing this. It's a very simple argument, because if the true number of days I'm going to ski is less than say $7, then I'm fine, I'm optimum. The only time I make a mistake is when I misjudge this thing, right? When I think that I won't ski for more than 7 days, but I actually do, then I end up spending twice the amount. Okay. This is a simple like scheme. It is deterministic algorithm, but there are improvements to that. You can with coins, you can get like 1 minus 1 over e, but let's stick to this for simplicity. Okay. And in fact, it's tight. We can't do better than this. Okay. So what about prediction? If imagine the ski instructor looking at me saying that, okay, you don't look like a skier. You're going to ski for like 3 days. You're going to either break your bones or give up or go back home. There is a machine learning model that looks at a person's profile on the past history and predicts, like, this is how much you're going to ski. Can we use that to improve the algorithm? Okay. So that's a scenario here. So if X is the true number of days and Y is predicted number of days, that's what the machine learning model tells you. You can think of epsilon to be like the prediction error of X. And just to set up the notation, we just call this to be standard competitive ratio, the ratio of the algorithm and the optimum. And to put this consistency and robustness in concrete terms, we call this algorithm to be beta consistent if it achieves a better competitive ratio performance when there is no errors here, and the error is 0. And if it's gamma robust, if the competitive ratio is always utmost gamma, regardless of how much error you make. So here is first attempt. Here's a naive way to use hints. I just follow the hints, right? If the hints tell me more than B, I just buy on day 1. Otherwise, I rent every day. Okay. This is a very naive algorithm, naive way of using the hints. So it turns out that this is not a good idea. If this is the analysis, what it shows is the algorithm performance is always utmost optimum plus epsilon. In other words, it is consistent actually, but not robust. You can easily throw the algorithm off by providing a very large error, which is not a desirable thing to do. Right? You might have a huge error if the machine learned model gives you like a higher, and the analysis like a simple case analysis. I'll skip it. So here is a slightly different, slightly more non-trivial algorithm. The idea is to use the hints, but tread them with some caution. Right? Like, and the caution is captured by some parameter we call lambda. What we do is, instead of buying it on like day one, we buy it on lambda times b. Like, don't buy it on first day, but buy it on some scaled down version of the b day. Otherwise, you buy on like b over lambda. This is the simple algorithm that uses the hints. And what I can show is that this algorithm is 1 plus lambda consistent and 1 plus 1 over lambda robust. It has all the nice properties. Okay, this is an easy thing to work out. And depending on how much I trust the ML model on Oracle, I can vary lambda and get this. So lambdas are kind of a hyperparameter that's outside the system. Okay, so this gives some hope of achieving both consistency and robustness by playing around with the algorithm a little bit. And that's will be some kind of a theme in the talk. Okay, so in fact, we can actually plot the performance, and the caution actually helps. So lambda is a trade-off between consistency and robustness, and small lambda means I place a larger amount of trust in the prediction, and therefore I get higher consistency. Okay. Okay, so now I'll come to the main result that I wanted to present, which is online linear optimization. So this is not a single paper. It's about, like, what I'm going to summarize is from about 5 papers that I wrote with a bunch of my co-authors, and it covers like various aspects of these things. It all appeared in the last maybe 3 years, 2 to 3 years. Okay. So let's abandon the comparative ratio concept and let's look at the regret one. That's what we're going to focus here. And this is what is called constrained online linear optimization. It's a very beautiful, extremely elegant setup. First formalized by Zinkovich way back. So here is a setup here. So assume that all the actions take place in a unit ball in d dimensions. So at every time step, the algorithm is supposed to choose a vector, WT. And after the algorithm makes a choice, nature responds with the cost vector C. And you compute the loss at this time step to be how much the algorithm's response and what nature says agree with each other. So the loss is the inner product of WT and CT. That's why it's a linear optimization problem. And the objective is to minimize regret. And the benchmark here is if we were to play the same vector W star at every time step and you compute the loss, how much would that be compared to the loss of the algorithm? So the best single vector W star is the benchmark that we compare against, and the performance of the algorithm over all the time steps, that's a loss, and you take the best, take the gap between that. That's the objective. That's the minimize regret. You want to minimize this point. It's a very nice problem. It captures many things, including portfolio selection, stochastic gradient descent, and every kind of many continuous optimization problems are captured by this formulation. There's a nice book of Elad Hazan. The whole book is devoted to this problem. Okay, so there is a classic algorithm called follow the leader, which is very, very intuitive. It's the algorithm is very intuitive for this problem, which is, think of this way, right? When an algorithm has to play a vector WT, what can it do? It has a history of all the costs that have appeared before. So it just picks the vector W that minimizes what I've seen so far. It's the FTL algorithm. So you pick W such that all my previous costs just compute what's the best W I could play given all the past history, and I just play that. And natural algorithm, it turns out that this alone is not enough due to some technical reasons. You need to add what is called a regularizer. So you also want to make sure that the W that you respond is not like too big. So you add some kind of a length regularizing term here, and that if you play this vector at every time step, it's called FTRL, then you can show that the regret is square root t. So the goal, the holy grail of this whole exercise is to achieve regrets that are sublinear in t, and in ideal world, logarithmic in t, right? The smaller regret you get is better. Okay, so that's the problem that we're going to look at. And this is a joint work with my collaborators and all the people actually, Aditya Bhaskara, who's a faculty at Utah, and Ashok, who's a faculty at BU, and my colleague Manish at Google. And here's a setup here. It's exactly same as before, except that just before the algorithm is responding with the vector WT, it receives a hint vector HT. Now, nature provides it with a hint HT. And the rest of the formulation remains the same. No, the hint doesn't play a role in the definition of regret or the causes, right? So it's a very simple setup. And the question now is, how much can the hint help? You know, can I relate how good the hint is with the regret that I get, right? And how should I modify the algorithm to do that? Okay. So to be able to do this, I need to define when is a hint good and use this following definition. A hint is good if it is sufficiently correlated with the cost vector that I have not seen, right? So remember, CT is going to appear later after I play the vector WT, and the hint is going to appear before I play the vector WT, right? So the hint is good if it is alpha correlated, if the correlation between the hint and the to appear cost vector is sufficiently large. So this is how the good hint looks. So basically all the hints here are good. And we believe this is actually a better notion than looking at distance and so on. This is actually a more robust notion. So people who are familiar with continuous optimization, there is something called optimism bounds that deal with distance notions, but we feel the correlation notion is better. It leads to actually better bounds. And the cost of a query cost of a hint is basically this quantity, the length of the unappeared, to appear cost vector regardless of its quality. So we don't care about quality, we just assign a cost to that. We don't want to just charge only the good hits, we want to charge all the hits. Okay. Yeah.
So this is one way to define the problem, right?
Yeah.
You could have another way which is dependent on W star. Like this hints are random perturbations of W star, or I don't know.
Yeah. This is not a unique way to define the hint. This is a good point. This is the one bug or feature, whichever we want to call it, is that this area is like you define the way you think the hints are reasonable, right? So that's people have done that actually, and that I think it's a feature of the problem. We're not stuck to like one notion. Okay. Now, of course, we are not the first to ask this question about sublinear. Okay, just to take a step back. So remember, like our goal is to get sublinear regret and ideally log regret. That's the real goal. That's ultimate goal of this. Because sublinear regret means the average performance, kind of approaches like a fixed benchmark W star. Right? So the original paper of Zinkovich and further like later by Bianchi and Lugosi, they argued that the regret actually is square root t and it's tight. In fact, it's obtained. It's they actually have a more general result, and the regret is tight even for linear losses. That's the hardest case actually. The losses strongly convex and so on, you get better regret bounds. So as I said, we are not the first to ask this question, though the earlier work didn't pose it this way. But there's a nice paper of Elad Hazan and Imran Megiddo from way back, not the 30s or 60s, but more recently, that if the first coordinate of the cost is known, and it is sufficiently large, if it has more magnitude more than alpha, then you can design an algorithm to get basically log regret. Right? But if you start at it, it's a very strict assumption. If I need to know the first coordinate precisely, and the first coordinate has to satisfy the strong correlation property. So more recently, this was relaxed a little bit by Offerdekel and his co-authors, who showed that if every hint is alpha correlated in the way that I defined earlier, then you can still get log T regret. So it's a very nice result. In this language that I stated a few minutes ago, it is consistent because if the hints are super correlated, you get good result, good regret, log T regret. But it's not robust because their proof and their whole argument depends on the fact that the hints are correlated at every time step, which is a very strict requirement, and definitely not parsimonial because they need hint at every time step. See, the first work that we did a few years ago, we were able to relax the result. So what we showed is that even if most hints are alpha correlated, you can still get log regret. In addition to shading this factor D, you do get an improvement in terms of making this result robust. So you don't need correlation at every time step. So there can be bad time steps where the hints are not correlated. And the result that we obtained was not parsimonious because we need the algorithm to know the hint at every time step. What I'm going to describe next is some ideas behind the algorithm that makes this consistent, robust, and parsimonious. So I wouldn't go into the original paper, but it's more recent work appeared in NeurIPS last year. Here is the main result and the bound. So there is an algorithm for online linear optimization such that if there are B bad hints, then it obtains a regret of roughly B times log T over alpha. So I'm oversimplifying many of the terms and O tilde and so on, but this is the spirit of the result. Okay. So let's start at this result. When all hints are good, that means like B is 0, now there are no bad hints, then you get back like log regret, which is exactly what you want, this consistency, right? So you want really logarithmic performance, then you have no bad hints. Okay. And robustness. Even if every hint is bad, every hint is adversarial, think of the hint being a random vector, it's useless, right? So B is T, you get like T log T over alpha. Actually, you can shave out the log T, but you can actually get square root T regret. So the algorithm is robust against like bad hits. And finally, you can show that the expected query cost is actually sublinear, it's square root T. So that's a summary of the main result that I want to talk about. Any questions? Everything's tight. Yeah, I'll come to that actually. So the question was whether it's tight, and then I'll give at least the bounds for the load box. Yeah, up to log factors. Okay, so what's the key idea here? The key observation is that suppose we have the following scenario. Okay, so you have this unknown cost vector in red, and FTRL makes a mistake. FTRL gives a vector that is not really correlated with the cost. So you're going to incur a huge regret at this step. However, the hints are good. The hints are well correlated. In this case, we really want to use a hint, right? Because hints are giving something that the FTRL is not able to give. So we want to use that properly. So in this case, the hints are better to use. You play the hint or minus the hint. And if for all the such time steps, we're able to play the hint. And if we know these things when they occur, then we can completely wipe out the root T regret from FTRL. So FTRL inherently incurs like a root T regret. So you want to be able to kill that off by doing this at appropriate time steps. That's the only way to remove that root T factor. Okay. So that's one case when FTRL actually fails. There's another converse case where FTRL does great. In which case, I don't want to use a hint, right? It's a waste of a hint query, and maybe a hint may be misleading in that step. So in this case, I should not use a hint. I should just play FTRL. And in fact, as I said, it may actually hurt using the hint. Right? And the main question is, how do we detect which of these two cases we are in an online fashion. So just as an aside, it turns out that there's a technical improvement to FTRL analysis one can do, which is if all the costs are basically linear, right? Then FTL already achieves like a log regret. This is an easy case for FTL. And you can extend this to FTRL as well. So the reason why I put this up is that we want to appeal to this result in order to be able to get to the log regret. And this will be a tool that we use as an intermediate step. And here is the outline of the proof. The first case is exactly what I said before, which is this is the case where the hints are great to use. So you need use the hints in this case to cancel out the FTRL regret. And the second case is where FTRL is better to use than hints. What we show is that if this really happens, then this roughly implies that the costs are actually linear, which if you appeal to the previous result I put up, improved analysis of FTL, you get like a log regret. So in both cases, you get a log regret. So in this case, by canceling out all the root T regret from FTRL, and in this case, by using some other structural property of the costs. And how do you detect these two things on the fly? Right? That's a harder, because individual case by itself, it's easy to understand, but how do we know which case we are in? And the main idea is to use another what we call the hint probability chooser, which is like an online gradient descent, which decides how much I need to trust the hint. So this is a black box. This is a box that spits out a probability, which says this is how much you should trust the hint. And this thing flips a coin. And if it comes out to be head, it uses a hint. If it comes out to be tail, it doesn't even ask for a hint. It just uses the guidance given by the FTRL algorithm. And then you compute the loss. Of course, the cost appears after that. Compute the loss and send the appropriate feedback to these two black boxes. One to adjust my choosing of the hint for the next time step, and also the appropriate feedback to the FTRL algorithm itself. And that's the whole framework. So basically, there is some kind of a recursion here. So you use another step, an online step, to decide which step to use. So somebody asked for lower bounds. Pretty much every term in this is tight. Remember, this is the bound that we have. You can get a square root b bound, you can get a 1 over alpha bound, you can get a log t bound, not in the product form, but we believe that's probably tight. And you can get query bound. Now you can't do better than square root t in terms of the query complexity. In fact, even more actually, we really need this probabilistic box because any deterministic algorithm, you can show that it gets log regret. We'll have to use linear number of hints. Can't hope to get sublinear hints and be a deterministic algorithm. Okay. I'll try to finish on time so that we are not late for lunch. Just to give you an idea, like how does a lower bound here look like? It's very simple. You create some kind of a random instance with the right expectation. It's a one-dimensional instance. So basically, at every time step with probability p, the cost is like p minus 1 is a number. And with remaining probability 1 minus p, it's just p. So the expectation is 0. But on the other hand, you can show that the benchmark that you play can be chosen in a smarter way, which is basically the sum of all the costs that you've seen so far. That's the benchmark. And if you just work some simple calculations out, then the regret is roughly like p times p, which by selecting p, you also know that whenever the hints are bad, then you get like a square root b here. So you can work it out so that you can square root b regression. And you can get a similar lower bound to 1 over alpha, except that now the action has to take place in 2 dimensions. So all the lower bounds are fairly easy. And how does it work in practice? So we tried, this is like a while ago, we tried on ResNet. So we used Adagrad and used hints. So hints turn out to be, at least for ResNet, it seemed to get better performance than Adagrad, but it couldn't beat Adam. But again, like we didn't try to optimize hyperparameters, or our notion of hints was just the previous gradient, or maybe even the history of all the gradients and so on. So we try to use that. But I think there's some topic that I'll be very interested in pursuing to see whether these ideas have any merit in practice. Okay. And there are a bunch of other extensions that one can think of. One is multiple hints. So imagine a scenario where I have 10 machine learning algorithms, and all of them feeding into this online algorithm, trying to tell like, go this way, go that way, and so on. So how do I reconcile? For this online optimization, you can show that there are k hints. You can get this kind of a bound where the interesting part is B is not the number of steps where the best possible hint is bad, but it's the best possible linear combination of hints is bad. And this is like a much stronger result, because a single hint by itself may be bad, but if I am magically able to combine all these hints into like it's a linear problem, right? So I can combine all these hints into like a different linear function, then maybe that's better, right? And this bound shows that you can actually get it. This is a subsequent work that we did. And we also looked at movement costs. Like, there are scenarios where you measure the movement cost of an algorithm. So the consecutive responses of the algorithm, the WTs that they play, how much they deviate from one another is part of the measure. And you can get like similar kind of bounds depending on the hints that you get. This is like a couple of years ago. And then more recently, this work that's going to appear in ICM like in a couple of months is where we looked at bandit feedback. So one thing that I swept under the rug was the feedback that you get from nature is nature gives you the entire cost vector, right? But in settings known as bandit settings, you don't get to see the cost vector. You only get to see the cost. You only get to see the loss, actually, the WT, CT, but not CT. Okay? And again, like square root regret is known for this. What we showed is that it's a slightly surprising result, that even if you get good hints at every time step, you cannot beat this. There are like simple two-dimensional instances where you cannot beat the square root regret. So basically, hints in this setup, as I explained before, they're useless. On the positive side, you can enhance the model. So instead of a hint, the algorithm can query the oracle. It can ask like, you can pick any vector it wants and ask, give me the correlation of the given vector with the unknown cost CT, give an estimate of that, right? It's a hint. Under this model, in fact, random vector works, you can get D to the, you can get log T regret. It's a stronger model, but at least if our goal is to get log T regret, it's doable. And the main idea is very simple. It's basically, by doing this oracle, you can get like an unbiased estimate of CT, which turns out to be sufficient to make the proofs go through. Okay. So I'll just quickly go over the caching setup in a couple of minutes. So this is the, that's all I have to say about the online optimization. But I want to give another example of where hints are useful, but this is more traditional, like combinatorial setting, which is caching. So the problem I'm sure most of you are familiar with. So you have a bunch of pages arriving, and then you have a cache of size k, and the goal is to select items to put them in the cache so that accessing them is easier later. Right? It's a classic problem, and the cost of the algorithm is how much I incur a cache miss. So if I want an element and if it's not in the cache, then I'm set to incur a cost of 1. This I can say 1960s. This is a very old problem. Belladi proved that in the offline setting, when I know all the requests in advance, there is an algorithm called furthest in future. That's the optimum algorithm for that. And the cost of an algorithm is just how much you deviate from this opt by this factor. You can take the same setup and throw hints at them, right? The hints can be, look at a page, when is it going to show up next? Right? That's a very natural hint. The rest of the stuff remains the same. And what we can show is that this problem has been studied reasonably extensively in the last few years. One of the first problems that I studied here. What we can show is that we can get a robust, consistent algorithm At the same time, the algorithm does not have to query at every time step. It can be careful in choosing which pages to ask for the time when it's going to arrive. So we can get a better trade-off. I'll skip those things. I'm happy to know. Talk offline. I want to conclude with a quick summary of what I talked. So we talked about learning augmented algorithm. Sorry, it should be consistent. So it's consistent, robust, and parsimonious. This is a field that's rapidly evolving, and I feel that there are a lot of interesting problems out there. One could view them through this lens. Algorithmic questions to explore. A particular aspect that I alluded to earlier is what about practical applications? I see that Kamalika is not here. So it turns out that in differential privacy settings, we did some work which actually is being used in practice, where if you have a prior on the data, right, which you can think of it as an ML advice, that can be used to improve the utility of certain privacy algorithms, provably, in both in theory and practice. So I feel that there is a lot of opportunities to improve, for example, ML training efficiency by casting certain problems in this framework. Because if you think about it, there's a lot of data out there, and historical data or like patterns that we have seen elsewhere and so on, right? How much of those things are actually usable by these algorithms is an interesting area to explore. And in fact, varying my old like complexity theory kind of hat, I feel that there is an opportunity to describe some kind of a P to the ML class where that describes all the problems that can be done efficiently and with good performance with an ML algorithm. With that, I conclude. Thank you.